Hello everyone, I'm Dr. Kang. So in this short video, I'm going to explain how the likelihood ratio test can be used in the case of a normal distribution example where we're interested in testing a null hypothesis of mu equals to a specific value mu naught against the composite alternative hypothesis where mu is not equal to mu naught. In both cases, we will let the variance be unspecified. So the first thing to do is to write down the likelihood of the sample under the null hypothesis. So here our mu is equal to mu naught under the null hypothesis. So our likelihood function is given by 1 over 2 pi sigma square n over 2 exponential summation xi minus mu naught, because mu has been specified, over 2 sigma square. And we want to maximize this likelihood function under the null hypothesis in order to find out the maximum likelihood estimator of sigma square under this null hypothesis. So we take the log of L, and this gives us the following. So we have minus n over 2 log 2 pi sigma square. So we take the derivative with respect to sigma square, and this gives us a simple form 2 sigma power 4 minus n over 2 times 1 over sigma square. And here we can multiply numerator and denominator by sigma square, right? So we set it to 0, and therefore our sigma square hat is given by this expression, all right? In the same manner, we can find the maximum likelihood estimator of mu and sigma square under the alternative hypothesis. And basically, under the alternative hypothesis, mu hat is equal to the sample mean, and sigma square hat is just equal to the sum of xi minus x bar square over n. So both of these results have already been discussed in the previous video about maximum likelihood estimation of the parameters of the normal distribution. So with these results, we can now specify the likelihood ratio. So the likelihood ratio lambda is given by the likelihood function that's maximized under the null hypothesis over the likelihood function that's maximized under the alternative hypothesis. And here we have 2 pi multiplied by summation xi minus mu naught square over n. So here we have x bar square over n, right? So here this would be minus n over 2. Then multiplied by exponential minus summation xi minus mu naught square over 2 times the maximum likelihood estimator for the variance under the null hypothesis, so which we found just now as the following. And similarly, we have this result for the denominator. All right, so here very easily we see that we can cancel off the common terms, so this entire term here becomes 1, and here we can also cancel the 2 pi's, the n, and this leaves us with the following result. So we have summation xi minus mu naught square over summation xi minus x bar square raised to the power of minus n over 2. So far so good. So now to proceed, we will use this following identity, whereby we write the quadratic form here as the following. So we subtract x bar and we introduce x bar again. So this gives us the expansion plus, so we look at the quadratic terms, and then there's a cross product term, twice of sum of xi minus x bar times x bar minus mu naught. Now it can be seen easily that the cross product term is equal to 0 because this term here is essentially a constant. So here summation xi minus x bar is basically n times x bar minus n times x bar, so you get 0. Alright, so we have the following identity, which we can substitute into lambda, and this results in the following. So once you have substituted, so we can divide by the denominator, so that gives us 1 plus the following result, right? Minus n over 2. Okay. So to proceed, we will use the Neyman-Pearson lemma. So that requires the likelihood function to be bounded by some constant k. Right? So what do we do here? So basically we can multiply both sides by 2 over n negative, so, and then rearranging, so we will get the following result. That would be k minus n over 2 so that's 1 over right, minus 1. Okay. Now, to proceed, we will note the following. So this form reminds us that of a familiar result, whereby the denominator here we can divide by n minus 1 and then cancel off with n minus 1. And rearranging, we will get the result so we can also rewrite here a little bit as so here's n, so this is s squared the variance, the sample variance. All right. Okay, so sorry, here's the square. Now, once we have manipulated the likelihood ratio into this form, then we are almost done. So if we recall that, so here on the left hand side we can write x bar minus mu naught over sigma over square root of n. We can take the square. Alright, so here we introduced sigma square, the constant, and therefore over here we have can do the following. So square root of s square, so we can square this as well, and we divide by sigma square, right? Okay, so this sigma square, so take the square root, so that's a sigma, that's sigma square, that will cancel with the sigma squared in the numerator, and then we proceed to multiply with n minus 1 and divide by n minus 1 here, right? So this is greater than or equals to n minus 1, k minus n over 2 minus 1. So once we have manipulated the likelihood ratio into this form, then it is clear that the numerator here has a standard normal distribution under the null hypothesis, because x is normal with mean mu naught and variance sigma square, right? So x bar will have the same mu naught, but with variance sigma square over n. So the standard deviation is sigma over square root of n. And how about this part? So this part, we know that n minus 1 s square over sigma square has a chi-square distribution with n minus 1 degrees of freedom. And if we recall that the t statistic, the following transformation, right? So if you have a standard normal random variable and you have a chi-square random variable with r degrees of freedom, you divide it by the degree of freedom and take the square root. This transformation will give us the t distribution with n minus 1 degrees of freedom, right? So therefore the left hand side is actually equal to the square of the t statistic, right? The square of the t statistic, and therefore the rejection region is specified by t squared greater than or equals to n minus 1 k minus n over 2 minus 1, right? All right, so we get this rejection region. So let's proceed. Let's clear some space here. Okay, so so instead of working with t squared, we can choose to work with the absolute of t, and that will be, so t squared greater than this term on the right hand side is equivalent to absolute of t greater than n squared, its square root, right? Okay, and this is equal to t alpha over 2n minus 1 for a test with size alpha, right? Okay, So our best critical region in this likelihood ratio test would be given by the following region. So we would have the region C, whereby so C, so the values of x such that the t statistic is greater than or equals to this critical value. All right. Okay. So this t is basically based on all your samples, right? Your x bar and your s square. Okay. So if you want to work out what the value of k is, so that only requires a little bit of algebra. So let's try it. So we take this part here. So we have n minus 1, k minus n over 2 minus 1 is equal to the critical value, the t critical value squared. So k minus n over 2 is squared critical value divided by n minus 1 plus 1, and then finally k is basically this term here, raised to the power of minus 2 over n. Or I could have made the, so please check this, was it 2 over n just now, right? Anyway, so you get the idea. All right. Okay, so that's the end of this short video presentation about an example in using the likelihood ratio test to perform hypothesis testing of the mu parameter in the normal distribution. Thanks for watching.